Estamos ao vivo? Acho que
Olá.
sim. Então, pessoal, bom dia a todos. Desculpe o pequeno atraso. Vamos, então, sem mais demora, dar início à palestra do Bruno Ribeiro. O Bruno Ribeiro ele tem uma trajetória muito interessante, muito legal. Ele saiu da UFRJ, fez graduação aqui, fez mestrado aqui no PESC, então, de certa maneira, é da casa. Depois foi para os Estados Unidos, fez o doutorado dele lá e decidiu seguir a carreira acadêmica dele lá. E nessa trajetória ele trabalhou com diferentes áreas, em diferentes coisas. Começou com redes de computadores, que é o tema do doutorado dele. Depois foi brincar com Network Science, que foi o primeiro pós-doc dele nos Estados Unidos. Não satisfeito, foi brincar de Data Mining na CMU com Christos Falutsos. Não satisfeito, começou a brincar de Machine Learning nos últimos 2, 3 anos. E não satisfeito, agora está fazendo Deep Learning, porque alguém tem que entender esse troço de Deep Learning. Então o Bruno falou, ninguém entende, eu vou tentar entender. Minha bagagem matemática vai ajudar a tentar resolver esses problemas aí de redes neurais profundas. O Bruno já falou aqui outras vezes, ele vem frequentemente ao Brasil e ao PESC. Então é um prazer ter ele aqui novamente hoje, num tema bem interessante. Eu estou super curioso para saber sobre o que ele vai falar. É um tema muito da moda, representação de grafos com redes neurais. Okay? E, bom, sem mais demoras, obrigado pelo aceitar o convite.
Obrigado, Daniel. É sempre um prazer voltar para a UFRJ. Eu tive várias aulas sentado nessas mesmas cadeiras. A minha palestra vai ser em inglês, vocês vão me desculpar porque acho que vai ser difícil traduzir. Eu vou falar sobre representação de grafos, Graph Representation Learning, and how probability theory has been helping us define a new class of representation models for graphs. And this is a joint work with my student Ryan Murphy and Bala, and also my collaborator Vinayak Rao from the Stats Departament at Purdue. So I'll start. So the question that we had when we started this, graph neural networks were very hot, and the first question that I had was, what is a graph, right? What are we trying to represent? What it really is. A graph, as a detail, it's a static and single layer graph, just one graph. Or you can say network if you do network science. So there are many examples of graphs. So a graph, you can say it's a set of vertices and edges, and you can have attributes on the vertices, attributes on the edges. We have biological graphs. Molecules can be seen as graphs, although a graph doesn't fully encode all the properties of a molecule. Social graphs, the web, and ecological graphs, etc. So I think I'm assuming that everybody here is familiar with what a graph is, right? Okay. So here is kind of a statistical view of a graph. The first. I think that the easiest representation of a graph is through its adjacency matrix. We have, first of all, we have this graph here. And now, from the graph, to build the adjacency matrix, we need to number the nodes, okay? We need to decide which node is node 1, 2, 3. And that numbering is arbitrary. You can just decide whatever number you want. And if you decide, say, node 1 here, this is node 1, then the connections, there is in this matrix, 1 represents the first row and first column of the adjacency matrix. And then if you have an undirected graph, this matrix is going to be symmetric. And the first row is going to encode the connections from node 1 to other nodes. So we have node 1 to itself, there are no self loops. The node 1 to node 2, there is an edge, so you put a 1 there, and 0 if there is no edge. And that way you can perfectly encode what you're seeing here in this, encode the edges and no edges, the no edges in the adjacency matrix. Okay, so, but the adjacency matrix representation requires a labeling of the vertices, which is arbitrary. So if you think about what is a probability model over a graph, it's just a probability over the possible adjacency matrices. Imagine all possible adjacency matrices. I give you a probability over that matrix, and you can sample adjacency matrix according to this probability. And that's all that the graph model is. It's just a probability over the possible adjacency matrices, okay? One thing about notation, when I'm using A1 dot, is going to be a row, and if I use dot 1, it's going to be a column of this matrix. Okay, so now I'm going to start slow and go and build up what a model really is. I start from sequences and then I go to graphs, okay? So first I'm going to define what a probability is, So consider a sequence of random variables, okay? We have 1 to n variables from some, for now, let's say a countable space, omega. And you can think of omega, say, the set of all possible words that you can have, okay? This countable space, in this case, is even finite. And we are going to define a joint probability distribution over this n words, all right? There's some probability. So a quick sequence example, we have this sentence here, and then the first variable is the first word, the second variable is going to be the second word, right? It's just a sequence. So any sentence is just a sequence of words. And we have a joint probability distribution of, with a word, with a sequence with 9 words, this is the probability that you would create this sentence. The joint probability is just a function. There is nothing else, but it's a function from this n-dimensional space with each coordinated omega to 0, 1. Just a function that maps some, say, sequence of 9 words into a probability, okay? There is a detail that things need to be normalized, but it's just a detail. Really, what's important is that it's just a mapping between n words, n elements to 0, 1. It's also important to see that the probability takes an ordered sequence, right? So if I change the order of the words, for instance, if I write quick the brown fox, the probability of this should be 0 because it's not grammatically correct, okay? So the order matters a lot, and probability distributions, joint probability distributions, order is very important. Now, what if you say, I don't care about order? I'll give you a set of random variables here, and I want to tell you that I don't care what the order is. I want to treat this as a set, not as a sequence. How should we define the joint probability distribution over a set? Remember that the joint probability takes a sequence and maps to 0, 1, okay? So how we define a set now? A joint probability over a set. How should I do it? There's some constraint that I have to place on P, right? What's the constraint? Nobody?
The probability of any possible sequence that those elements is equal is always the same.
Yeah. So yeah, it's you got epsilon close to the answer. That is a probability distribution P is such that if I reorder the elements, the variables, the probability has to remain the same. Okay. So for any permutation of these variables, the probability is always the same. Okay. So that's how we define a probability distribution over a set. And therefore, this function, this P now, is what we call permutation insensitive or symmetric. I don't like to use the word symmetric because people think symmetric means something different. But it's just a symmetric function. And this notation here, pi of 1, so pi is a permutation of these numbers, and pi of 1 would be the first element of this permutation, okay? And pi n is going to be the last element of a permutation of these numbers, the sequence 1 to n. Okay, so that's it. We just need to make sure that P is permutation insensitive. And there are some very useful references for this. We have a paper I clear describing this also, but also Diaconis has a very nice paper on on what this means in terms of probability theory. So let me give you examples of sets of random variables, point clouds. When you measure, when a self-driving car has shooting laser to get measurements of distances, it's called LiDAR. And LiDAR will see a picture like this. Okay, it's a 3D map of the world. And each laser, it's a rangefinder. It finds a distance to a specific point. So it shoots many lasers, keeps spinning, shooting lasers, and then finding distances to many different objects. And an object here is going to be a set of points, okay, in the 3D space. So here, this is an airplane, for instance. You can think of like a bag of words. If you jumble up all your text, this would be a set of words. And your friends are also a set. There is no specific ordering of your friends, right? You can just treat them as a set of friends. So there are many types of sets. So a lot of the functions that we want to compute or models that we want to learn are over sets. Okay, so now let's go from sets to arrays. Sets is a one-dimensional object. Well, maybe, yeah, not important. So arrays will be, in arrays I'm going to get the same variables, but now instead of just having one index, I'm going to have two indices. I could have more, but let's put just two indices. And I'm going to define my probability distribution. It's a little more complicated, but it's like this is the set of all possible pairs of indices, okay? All possible pairs of indices of any size. So your function takes some pairs of indices. Let's say if you have 4 here, it goes from x11 to x44 and all possible values. And then maps that to 0, 1 again. Okay, and remember this is ordered. This needs to be ordered because it's a probability, it's a joint probability. Now, I'm going to make this definition. I want this to be symmetric or permutation insensitive in the following very specific way. I want the permutation, if you apply, you have to apply the permutation over the indices separately. But it's the same permutation, okay? So x11 is going to go to x pi 1, pi 1, okay? And I want this to be the same probability, all right? I'm defining what this is. I'm just telling you what the definition is. So that's perfectly fine. We call this partial exchangeability because variables can exchange, but only partially. It's not possible to exchange them. They're using all the same permutation here, so there is a constraint. So what I'm going to say is that the P, this P here, is a model of a graph. And any graph can be modeled this way, okay? Any graph where you don't care about the labels, right? The adjacency matrix is created by some assignment of labels that is arbitrary. A model over that will be have exactly this property. And that's the only property you need for a graph model. A statistical model of a graph only needs this, nothing else, okay? For each graph, P assigns a probability. You can think of this X as the edges, right, of your adjacency, you can think of this X as your adjacency matrix, okay? And X11 is going to be the edge of the first node to itself. So it's trivial to add node attributes to the definition because X here is from some space that I didn't define, so you can have edge attributes. You can even have node attributes, easily adding node attributes to this definition here, but that's not important. If omega is 0 or 1, is a set 0, 1, then P is a probability distribution of adjacency matrix, as I was showing you that it's a definition of a graph model. So is it clear what the graph model is? Right? I just need to make sure that this function is permutation insensitive. Okay. Let me explain, show a little bit in graphically what it is. Right? So here we had our original adjacency matrix. And now I have a permutation. I changed the labels of 1 and 2. I permuted these numbers. And now node 1 maps to position 2. So it's going to go to the second row, second column. Okay. Node 2 now maps to position 1 in pi. So it's going to go in the first row, first column. Okay. So I just permuted 1 and 2 in the adjacency matrix. And then the graph model is invariant to permutations, meaning the probability of A is the same as the probability of A pi pi. And I'm going to represent this as A permuted according to this permutation pi. Okay? All right, so everybody with me so far? Okay. So invariances are actually look very simple, but they have impressive consequences. So let me show you one that I like quite a bit. Have very deep implications in nature. I'll give you an example. Familiar with Noether's first theorem? Anybody familiar with that? She wrote this theorem in 1918, and showing that invariances imply some law of conservation. Okay? Always, whenever you see an invariance, it means some law of conservation. Something is conserved. For instance, time and space translation invariance implies energy conservation. The fact that when you make an experiment, it doesn't matter when you start, it doesn't matter where you start. Okay, if that's true, then it must be that energy is conserved in your experiment. That's the definite implication. Just starting from an invariance that no matter whatever experiment that you do, no matter when you start, and no matter where you put it, if it's in this table or this table, if it doesn't matter, implies energy conservation. Okay? Just from that invariance. So I don't know if you have tried, right, to see energy conservation in practice. It's quite cool, right? Yeah. Do you know these balls that you... Mm-hmm. Okay, so the study of because it's such a has such fundamental implications, the study of probabilistic invariances, you can imagine, has a very long history. Laplace's rule of succession dates to 1774. Maxwell's work in statistical mechanics, 1875. And permutation invariance for infinite sets has this really beautiful theorem from Definiti in 1930. For the specialists in the room, it's a special case of ergodic decomposition theorem related to the integral decomposition. There is Orbans and Roy have a really nice overview of how this works. And if you really love invariances, I highly recommend the Kallenberg's books, because Kallenberg has done some amazing work on invariances, probabilistic invariances. Okay, so now I'm going back to, I guess forward, that was in 1930s, right? Moving forward to 1981, where Aldous wrote this really cool paper, Representation for Partially Exchangeable Arrays of Random Variables. And I'm going to explain what he wrote on that paper. Now imagine that you have, remember that array, right? That's the variables with two indices. What happens if there are infinite number of such variables, okay? So that it's invariant, the probability is invariant to permutations, but there are infinite number of variables now. There is a very, what happens here is that because it needs to be permutation sensitive and infinite, there is a very strict condition that imposes on the probability, the structure of the joint probability. And this implies, this being infinite and being permutation invariant here implies the following. You can write this probability distribution as a mixture of independent observations, okay? So let me give you how this would work in practice. You get a node I, you sample a uniform. Get a node J, sample another independent uniform. And now we have a function that links these two values to a probability of having an edge ij. Okay? Given this representation of I and this representation of j, which is a number that you drew randomly uniformly, right? Just uniform between 0 and 1. All the edges are independent. The probability, the joint probability, this joint probability here decomposes into independent observations. Okay? Edges are all independent given this representation. And this is a fact. I mean, this implies this implies this. It's an if and only if condition. All right? Which is very cool because it shows you that if you have a representation of node I, a representation of node j, you can consider all your edges independent of each other. And that's basically, if you think about any graph model that you are familiar with, they all make this assumption. All of them, because we don't know how to optimize without that, basically. So it's a mixture of uniform distributions, okay? It's a mixture model, actually. All right, so the one important thing is that the Aldous-Hoover completed the Aldous theorem, so that's why it's called Aldous-Hoover representation theorem. The representation is sufficient only for infinite graphs, okay? So it really is the best you can do. This representation is, there's an equivalence only for infinite graphs. If graph is finite, then you could possibly have more powerful models, okay? But this is sufficient only for infinite graphs. So let me give you so I've been talking, now here we call the Aldous-Hoover representation theorem, and I've been talking about these values here being a representation of node I and node j, right? So what's this, what is this word, representation? How does it connect to the probability? So let me explain quickly. The relationship between deterministic function and probability distributions are given by some really cool tool in measure theory called noise outsourcing. And the idea is the following: if we have any probability distribution, conditional probability distribution, probability of y given x, it can be represented as y equals to a deterministic function, that takes x and takes epsilon, which is uniform independent noise. Okay, so the uniform variable here. Okay, any probability distribution can be described, conditional can be described that way, with a deterministic function. So why it's called noise outsourcing? Because all the randomness is entirely outsourced to epsilon. Okay, there is no randomness in the function. So a representation of x, what we are going to call Sx, is a deterministic function that makes y independent of x given s. Okay, if I give you Sx, I don't need to give you x because I gave you all the information that you need to know to determine the probability of y. Then in this representation, we can say that exists a g such that instead of using x inside g, I can use Sx. Okay, there is a g that is true. Instead of using y, I can just use Sx of g. Okay, because all the information that I need for y is encoded in Sx, and that's what we call a representation of x. In statistics, if you're familiar, you can say a sufficient statistics. Sometimes we would call it sufficient statistics of x. But that's for estimators, so I don't like it very much. We generally call this just a representation of x. Okay? Is that clear? Okay. So if you heard deep learning, you can replace that sentence, deep learning, with learning representations. Because that's what deep learning is doing, is trying to learn these representations. Who here is familiar with GNNs? GNNs? Have heard of generating images, right? You know how it works? You're learning a deterministic function. You give random noise, it generates a new image. That's what a GNN is this learning this function here. Okay? All right, so okay, so now that we have an idea how representations are related to probabilistic models, let's look at the a very common Aldous-Hoover type representation in graph analysis. We start with this Gaussian linear model, okay? So we have a node I, and node I has, now you probably have starting to feel that this is familiar, right? Node I has a following representation, is a multivariate normal distribution with zero mean and some variance, okay? I'm sampling, I get a node I, and I say I'm sampling a multivariate normal distribution. And in my model, I'm going to say that the adjacency matrix, now if you say, is adjacency matrix 0, 1? No, it's not, because it's going to be normally distributed, but then we can revisit this again later. So Ij, right, the edge, the weight of the edge Ij is normally distributed according to the inner product of these vectors, okay? This is a vector, right, and then is the inner product of these vectors gives you one value, and then it's a normal with some variance, okay? And that's how I'm defining my model. This is a model for me. You can see that's very, very similar to the Aldous-Hoover representation theorem, right? The probability of an edges being independent, they're all sampled independently from this normal, given some representation of node I and node J, all right? So the question then, if I give you a matrix A, what's the most likely U? And U here is I'm going to put all these values, U's here in rows, and I'm going to make this a matrix, okay? So it's a matrix of these representations of all the nodes. The answer is maximum likelihood estimation, right? You can, if I give you A, you are looking for the U that will maximize the probability. What's the U that will maximize the probability of what I've seen, right? This matrix that I have seen. And then it's going, argmax means that you're trying to find a U that maximizes this, and that's going to give you a U star, okay? This is just maximum likelihood. So the equivalent optimization is to minimize the negative log likelihood. Minimizing the negative is maximizing. The log doesn't change the optimal point of the function, so it's log likelihood. So, and if you apply, the probability here is just a bunch of normals, and if you apply the log over this bunch of normals, you get some expression like this, plus some constant that doesn't depend on you. What you're trying to do is to minimize the square error between U transpose minus A. Plus, there is some penalty of having U too large, okay? U has to be, tends to be small, so that you sum the square values of all the values inside U, and then you're trying to also make sure that those values, those squares are small. This is what you are minimizing, which is exactly this, okay? The same optimal point is the same optimal point here. Have you seen something like this before? Right? Probably familiar with this. So remember this expression. We are going to come back to this later. Now I'm going to talk about something completely different that will turn out to be the same. Okay? Who here has seen matrix factorization? Has heard of it? Right? You've seen it? So you're trying to approximate matrix A with some U transpose, right? And U dot I is the ith column of the vector U, the column vector of U, of the matrix U. A good way to understand the composition is like this. You are doing this outer products here, and this creates a rank 1 matrix, and you're adding multiple rank 1 matrices. So depending on how many columns of U you have, it will be the number of rank 1 matrices that you're going to add, okay? To reconstruct A. Oh, here should be approximately. So the optimization problem is like this. You're trying, matrix factorization is used to compute a low rank representation of A. Have you done PCA? Right, so PCA is an example. It goes something like this. It's a reconstruction, it's seen as a reconstruction problem. You want to approximate, and finding the U is one that minimizes this square norm. we generally put some what we call regularization to make sure that the U is, actually it conditions this better, this optimization better if you do this. And also you tend to find a little better solutions. But in any case, there's a regularization strength here, there's a U here, but mainly you're optimizing the reconstruction, right? So you're reducing the square error between your reconstructed U transpose, and A. All right? Well, we have seen this exact equation before. It was our normal distribution model, right? It's exactly this equation here. Same equation. So the first thing is, if you are using PCA, or if you're using any of these methods that are minimizing the square error, if your matrix A is 0, 1, you are making a statistically incorrect assumption. Because what you are trying to reconstruct, you're assuming that the A is sampled from a normal distribution. So it can have negative values, can have positive values. It's not just 0, 1. So if you ever see anyone doing this for a binary matrix, just tell them that it's a wrong statistical model, okay? So this is a representation, and so you can see that everything that we talk about, when we talk about representations, there is usually an attached probabilistic model related to that representation. So if you see matrix factorization as an Aldous-Hoover representation, remember that I said it's an Aldous-Hoover type of model, right? That normal model. Remember that it's sufficient only for infinite graphs. It means that matrix factorization is not sufficient for finite graphs. It's not as powerful as it could be for finite graphs, because it makes these independence assumptions that are only necessary for infinite graphs. So what should we do then? Let's try to find more expressive representations for finite graphs. Okay? And here I come to graph neural networks. Who has heard of graph neural networks before? One? Just one? Two? Three? Okay, then you are going to learn everything you need to know from graph neural networks in 2 slides. Okay? And one of the slides is the tour. Isomorphism test, right? You want to test if 2 graphs are isomorphic. Again, the tour. So, who here is familiar with the Weisfeld-Lehmann algorithm? One? Oh, we have a disjoint set of people that are familiar with graph neural networks and the Weisfeld-Lehmann algorithm. So it's a recursive algorithm to determine if 2 graphs are isomorphic. It's a valid isomorphism test for most graphs, but not all graphs. So here's the algorithm. It's actually quite simple. Let HV be the attributed vector of vertex V. So if your graph doesn't have any attributes, you just assign 1 to h of vertex V. Okay, just assign 1. But if there are attributes like here, then you can put the attribute values. These are not node labels. Okay, these are attributes of the graph, like your age or something. They need not to be unique. And then the Weisfeld-Lehmann function creates fingerprints for the nodes. For each iteration, you're going to iterate over all vertices, and you have a hash function that takes the current representation of node V, okay, the current attribute, and then looks at the attributes of the neighbors, and hash that into a new value for the current node, okay? So takes yours, takes node V's, take attributes from the neighbors, and then it's going to hash into a new attribute for node V. You do that for all vertices, and then you iterate here until it converges. Most cases it converges. Hamiltonian cycles create problems, but let's say that it converged, right? So once you converge, we can prove that if 2 graphs are isomorphic, they are going to converge to the same values. So the nodes that are isomorphic in the graph will have the same value, and 2 isomorphic graphs are going to have the same set of ages, right? Which we can call fingerprints or attributes. Okay, once it converges, you know these 2 graphs are going to be You can see that they are not isomorphic here, and then you end up with different labels for these nodes, right? Although in this case, it's the same, well, that's okay. So you can see that you have here you have 1, 4, and here we have 1, 4, but only here have 2, here just have 1. So this belongs to a class of color refinement algorithms where the colors are these hash values and converse to unique assignments. Neil Immerman and Kai proved that examples that cannot be distinguished by this algorithm. And then the final hash values encode some structural rows of vertices, right? It often fails for graphs with high degree of symmetry, like chains, complete graphs, tori, stars. Okay, so here's the graph representation idea, okay? What is the hardest problem that we can have in a graph? One of the hardest problems is the following classification task. I give different tags for each graph, okay? Such that isomorphic graphs should have the same tag. All right? So two isomorphic graphs need to have the same tag, but all graphs have different tags. And now I want a machine learning algorithm to classify the tags. Given a graph, what's the tag? So given adjacency matrix, you want to predict the tag. So what you need is to find a representation SA such that G of SA plus some pure random noise is going to give the probability of the tag. In this case, the random noise is useless because this is deterministic, right? We have for each graph, we have a tag. So this representation needs to be expressive enough that for each graph, what it means is for the representation of the matrix, adjacency matrix A has to give the same representation to isomorphic graphs, so any permutation of A needs to have the same representation, and different representations to non-isomorphic graphs, so that this function here can take these different representations and map to different tags. Does that make sense? Yes? Okay? Okay. So this is very important, and this is what we are going to guarantee. So one thing that you can see is that the Weisfeller-Lehmann algorithm guarantees this. It doesn't quite guarantee this, but it's okay, right? It's okay. So we can try to use that algorithm now in deep learning. Let me give you the deep learning version of the Weisfeller-Lehmann algorithm. And this is absolutely everything you need to know about graph neural networks. Nothing else. So let me go straight to the algorithm. Remember the hash function? You get your own value, and you get your neighbors, and you get past the hash function, and you get a new value. Replacing the hash function with a neural network. And that's all you need to know. There's nothing else. That's what a graph neural network is. Now there are some details. First is neural networks, like probability functions, joint probability distributions, they take ordered inputs. They don't take sets. So this operation here, which I'm calling pooling, I have to get the representations of my neighbors and create a representation, right, for that set. Remember the sets that I talked about that needs to be permutation invariant? This function, whatever it is, needs to be permutation invariant over these values. Okay, so if I put these things in a vector, it needs to be invariant to those permutations. We have a paper at iClear exactly showing what's the most powerful possible machine learning model for this type of functions. Okay. And then the optimization is really, so you have some parameters here, some activation functions. It's not important. This is trying to reproduce the hash that I was showing you. And then what you do in the neural network, you try to optimize, find the parameters that will minimize the error of trying to label the graphs or whatever you were trying to achieve, okay? So that's what it is. So a paper this year at iClear also was showing that the GNN representations can be as expressive as the Weisfeller-Lehmann test. And the proof is quite simple, is that just that the neural network can emulate what the hash function does. Okay? Doesn't mean that you're going to learn that. It just means that it could, if you could, find the right parameters. But it will sometimes, by construction, a graph neural network is guaranteed permutation invariance because the Weisfeld-Lehmann test guarantees permutation invariance. So if I give you a permuted version of the adjacency matrix, it gets the same representation, okay? But the Weisfeld-Lehmann test sometimes fails. This is a family of circulant graphs, and these are examples of graphs where the Weisfeld-Lehmann test is going to give the same fingerprints to all the vertices, even though the skip links here is of length 2, is skipping 2, and here we are skipping 3. Okay? These are different graphs. They are not isomorphic. But it gives the same fingerprint. So the graph neural network is going to fail on these graphs also. So because of that, the question is, are there more expressive graph representations? You can see that the problem is similar to the graph isomorphism problem. Okay, so let me show our work then. So what we call relational pooling, it's just accepted the ICML. A is a tensor encoding an adjacency matrix and attributes. You can just think of A as an adjacency matrix. There are some node attributes also encoded in X. And pi, capital Pi is going to be the set of all permutations of the vertices, okay? Then F arrow is going to be any permutation sensitive function. So this is not permutation insensitive. This gives a permutation sensitive. Change the permutation of A. The F is going to possibly giving you a different value. May or may not, okay? Then if I create a function, F double bar, that sums over or averages over all possible permutations of this function that's permutation sensitive, this F double bar is permutation insensitive by sheer brute force, right? Okay? So that what we show is that this then is a necessary and sufficient representation of finite graphs. It means that for any finite graph, any probabilistic model of finite graphs can be represented this way, and more than that, a neural network can do it. Okay? So this is the most expressive graph model we ever had. There is nothing more powerful than this. Any finite graph distribution you can represent. Okay, so now we can say, oh, that's very nice, but that's totally useless. Because this, all permutations of the vertices only works for really small graphs, right? You cannot do that for large graphs. But one thing that's important, I think, in computer science generally, is for us to know what's the best we can do. And then we can try to then approximate the best. And then we will know how far we are, right? So this is the best we can do. So what we can try to approximate is to do the following. There are actually 3 ways to deal with this intractable sum. One way is for us to have a canonical orientation of the matrix, which means think of sorting the vertices in some way, okay? And once you sort the vertices, the output of this sort function is going to be the same. You get the same adjacency matrix no matter which permutation you gave, okay? The second way to make this sum tractable is to assume k-area dependencies. Statistically, we are saying that k by k, the nodes are in the observations of the edges for the nodes are independent. So the nodes are k by k independent, okay? If you are familiar with graphical models, forget graphical models. Graphical models cannot encode this. They're incapable of Bayesian networks or Markov random fields. They cannot encode this dependencies. So what F is going to do is consider just the first k nodes of any permutation. I'm going to explain this. And the third tractable way is through a stochastic optimization. We are just going to try to optimize this anyways. Okay? So let's look at the first tractability approach, which is this canonical orientation. We can order nodes with some sort function. Say, familiar with PageRank, you can order by PageRank the nodes. Suppose you have some, suppose for now there are no ties. I can explain offline what you do with ties. So we arrange A with sort A. And we replace this thing with sort A, pi pi, okay? once you replace this with sort A pi pi, because it's independent of pi, this comes out of the sum, and you just need to deal with one, right? With one adjacency matrix, because it's the same for any permutation. A lot of people have tried to use this. My advice is don't. The reason is it's very hard for you to come up with a sort that it really works for your problem. Most times we come up with sorts that are terrible, even page rank, whatever you want to do. It's not, sometimes it works okay, but there are better ways. We now understand what we are trying to do, so there are much better ways to do it. The second way is structability through Canary dependencies. I'm going to say that nodes are k by k independent, and then f considers only the first k nodes. What it means is that f, we have the sum over all permutations here. So if f only considers the first k, is like you get the permuted matrix and you just look at the first k by k square, okay? And you give that to the function. You look at the first k by k square, give the function. Look at the first k by k square, give to the function. Note the following. Here, these are the permutations. This is the original sequence. I permuted 1, 2, and 1. It makes a permutation here. If f is sensitive to this permutation, then the values for this function and this function will be different. But I'm looking at the same nodes, right? 1, 2, and 3, the original 1, 2, and 3 nodes. Okay? Because they are here. 1 and 2, just replace one, switch 1 and 2 here, but it's the same. Okay? The matrix is different now, you see? The matrix is slightly different, so it could affect that. But here, and this, you see it, here I permuted 2 and 1, and 8 and 7. But notice, because my function only takes this part, the permutation of 8 and 7 is not important. It gives the same value for this and this. So there are a lot of permutations that don't have to consider because they are repeated. Okay? And then what we end up saving a lot of computation because we only need to look at n choose k permutations instead of all the n factorial permutations. So the last approach is structability through stochastic optimization. This, unfortunately, I don't have a super good description that if you are not familiar with stochastic optimization, it might be a little difficult to follow. Standard stochastic gradient descent, you sample like a set of examples, you compute the gradients, and then you follow the negative gradient, one gradient descent step. So you basically, stochastic gradient descent is like you get a very large data set, you sample part of it, you do a gradient step over just that part, and you can prove that eventually this is optimizing over the entire data set. So we propose PESC-COPPE where not only you sample parts of the examples, but you also sample one permutation of that sum, just one. And you just optimize that one permutation. At each gradient step, you optimize just one permutation, sample randomly, okay? You compute the gradient, do gradient descent as if the sum never existed, you just sample one permutation. So what we can show is that this is actually a proper stochastic optimization procedure. If the loss function is convex, like the mean square error, cross entropy, negative log likelihood, which is basically all the functions, loss functions that we use in deep neural networks. This is a statistical model, right? The negative log likelihood is what we generally minimize. Then this procedure of sampling, updating gradients with sample permutations is an upper bound of the loss and gives you the following, the original model that you wanted. It's a bit detailed, like I'm not going to go in details, but the thing is, by sampling one permutation and optimizing, you're actually optimizing the sum, upper bound of the sum, so you're doing a proper variational inference procedure, which works, right, in most cases. It's an approximate, you're going to learn an approximate model, but most of the things we do in machine learning are approximate models anyways. So here is, then you can say, okay, so that's fine, but what is this useful, right? Is building this permutation-sensitive graph models useful for anything? So consider, for instance, the state-of-the-art graph neural network that was published this year. By definition, and let's call that state-of-the-art neural network F arrow, okay? And by definition, F arrow is going to be insensitive to permutations because the Westphal-Liman test is insensitive to permutations, right? Of the adjacency matrix. What we are going to do is to make F sensitive to permutations by adding the node ID as a feature. Remember that the node IDs were arbitrary? I'm going to say it's actual feature, useful feature of the node. So the graph neural network is going to look at the feature and use it as if it was important. But it's arbitrary, okay? So I'm going to put this as node features, but then I'm going to sum over all possible assignments of these IDs. Therefore, the final function is going to be insensitive to that fake attributes that I added, okay? It looks like, why am I doing this? So the reason is that we can prove that this new model is more powerful than the original model. It can identify every single isomorphic graph that the original Westphal-Liman test could, and more, and graphs that it could not. For instance, remember those circulant graphs that I was showing that the Westphal-Liman test cannot distinguish? If you add unique IDs, then you can identify them, differentiate them. And the reason is, fundamentally, the original Westphal-Liman test had the problem is, if you have a friend, and I have a friend, and Daniel has a friend, we don't know if it's the same friend or if it's a different friend. So suppose that we both have a Chinese friend. Then it's not clear from the hash function that the Chinese friend is the same friend or different friend. But with the unique ID, I can tell from the ID whether the friend is the same or not, okay? And that allows the function to be more expressive. But then in the end, I'm going to sum over all permutations, so I'm going to make this functions permutation insensitive again. And what we can see is that once we try to learn with the original model over these graphs, it gives random predictions to try. So we're trying to predict if it's L2 or L3 or L4, the different types of circulant graphs. And the original GNN is not capable of doing that, it gives random predictions. But doing this with permutations, adding permutations as features, then we can identify, we can better separate with the different types of graphs. And the optimization that we do to do this is that stochastic PESC-COPPE, stochastic gradient descent with permutations. So you can see that what's happening here is that the model is more expressive, but then we're only learning it approximately. But even then, you end up having a better graph model. And if you go to do the same for molecules, we can improve another GNN to predict the property of molecules, okay? With the same idea. And what's interesting is that this idea of using permutation-sensitive functions and then make them insensitive is interesting because we have a whole new class of graph representations. We can use sequence models like recurrent neural networks we use to learn text, right? We can use convolutional networks, treating the adjacency matrix as an image. It's fine. It's permutation dependent, but then I sum over all permutations and I'm okay. And I know that I can learn this approximately with stochastic optimization, so I'm fine. So these are all valid representation graph models for, basically now we have another playground to play, right? So the question that I have, which we don't know the answer, is are there classes of permutation-sensitive functions, F arrow, that will give better graph models than the models we currently have? For all these years so far, we have been doing graph models that by hand are defined to be permutation sensitive. Now I'm saying there is a whole new class of graph models that are permutation sensitive, and we can make them permutation sensitive. And we can learn them with stochastic optimization. Can we have better graph models than we ever had before? So as a take home here, this idea of relational pooling provides a new class of graph representations and models. Until now, we have been hand designing, right, these graph models to be permutation invariant, but we show that permutation sensitive models can be more expressive at least for some class of models. But the trade-off is that you can only learn them approximately. So if you think about this, this is what the playground we had for graph models so far, and we've been playing here, right? What I'm saying is the playground is actually this one. And we can have any function instead of permutation sensitive invariant functions, right? The only problem is that here, the original model, we learn the exact function is an exact invariance. Here, we learn the function approximately. And when we try to use the model, we will not be able to do all the possible sums. So we can do that by sampling and averaging, okay? By Monte Carlo. So we are only going to get an approximate invariance. But in machine learning, most of what we are doing is learning approximate invariances anyways. And whenever we had gone from hand-designed features to trying to learn approximate invariances, the performance has improved impressively, okay, in the past. So now we have, my question is that true also for graph models? So what we have done is we got models that were permutation invariant, and we moved a little bit here, and we saw better results. But there is a whole class of permutation sensitive functions that we haven't explored yet. So this is an entirely new playground to play. And if you have any ideas of possible permutation sensitive functions that could be useful for graph models, just let me know. So here's my information, and thank you for your time.
Obrigado, Bruno. Perguntas, comentários? Quem quer começar?
Muito obrigada pela palestra. É importante a gente aprender estruturas, né, com redes neurais. É legal isso. Eu queria que você comentasse, ao fazer essa ampliação do gradient descent, no aumento de complexidade do algoritmo.
O algoritmo, a complexidade do algoritmo per gradient step é minúscula, o aumento é muito pequeno. O problema é que leva mais gradient steps agora para convergir. É mais difícil porque a cada gradient step você está recebendo um input muito diferente. E isso faz com que a função tenha um pouco de dificuldade de aprender uma invariância, né? Então demora mais. Até o momento a gente só consegue fazer com grafos de tamanho 200 nós, 300 nós. Eu acho que para poder ampliar para grafos muito mais maiores, né, a gente vai ter que entender melhor como é que a gente deve desenhar essas funções para serem mais fáceis de convergir mais rápido na otimização. Não é uma complexidade per step, é uma complexidade de leva mais tempo para convergir.
É como se tornasse mais difícil.
Mais difícil o problema, exatamente. O penalty, o trade-off é que a função agora é muito mais complexa e você está tentando aprender aproximadamente. A vantagem é que a função é muito mais complexa também. Entendeu? Então é tanto uma desvantagem quanto uma vantagem.
Será que você não pode fazer a convergência sem permutação e aí começar as permutações? Você tem uma ideia melhor do ponto inicial?
É uma boa pergunta. Você poderia começar a convergência sem permutação e depois começar as permutações? A resposta é não. O motivo é que o que vai acontecer é que a rede neural vai pegar que o ponto ótimo de equilíbrio para o Stochastic Gradient Descent vai ser aqui, e para uma permutação só pode ser aqui. E aí depois, o loss surface de uma rede neural é muito flat. Desculpa, eu tenho que falar inglês. It's too flat for you to move from here to here. You won't be able to find this other point. So it's not useful. What it means is that you optimize, and then you start optimizing with the permutations, and you totally forgot what you did, as if you started at random. So it's kind of a waste of effort.
Perhaps you have grounds for parallelization.
Yeah, exactly. There is a very good point, right? Because this sum here, you can do multiple steps of the gradient and try to reconcile them. So distributed optimization really could be an interesting way of trying to deal with these models.
Eu tenho uma pergunta.
Sim.
Vou fazer em português.
Fala em português.
Então, você botou essa diagrama aqui, né? O verde tem as funções que são invariantes à permutação.
Uhum.
E aí você considera uma função f que é variante à permutação.
Uhum.
E aí você soma sobre todas as permutações, construir f duas barras que é invariante à permutação.
Sim, sim.
Minha pergunta é se esse f duas barras não está não tá dentro do verde.
Não, o que não
E assim,
aqui foi um pouco informal, mas quando eu falo f, é f de uma classe.
O seu f aí é o f que está dentro da soma ali, né?
Esse f da soma, mas é o f de uma classe. Por exemplo, uma Graph Neural Networks, all possible Graph Neural Networks. Não é o f qualquer, porque um f, entendeu? Não é todos os possíveis.
Você estava falando assim, a gente sempre trabalhou com funções que são invariantes de permutação. Você está dizendo que se eu trabalho com funções que são variantes, isso tem um poder de fogo maior.
Sim. Para uma determinada classe de funções.
Mas a gente está construindo uma invariância.
Sim. Mas,
fala um pouco sobre isso, porque isso está... Entendeu?
Eu estava tentando não entrar nesse detalhe, mas obrigado.
Porque isso é muito legal.
Não, pensa numa classe de funções, certo?
Uhum.
Uma classe. Nessa classe, eu posso pegar essa classe e fazer uma outra classe que tem essa classe como um subset, certo?
Uhum.
Mas não são todas as possíveis funções, é uma função de uma classe maior, certo? E aí eu pego essa função dessa classe maior e faço ela invariante, ou seja, ela é permutation invariant de uma outra classe maior, entendeu? É porque não é para qualquer função, é para classe de funções.
Então, assim, um takeaway que existem classes de funções que são invariantes, que são mais poderosas do que as classes que a gente vem
a gente vem tratando.
Porque o que você construiu é invariante.
É invariante.
Mas é um invariante compostas de coisas que são variantes.
Exatamente. Porque o que a gente tem feito, basicamente, a gente tem, já do início, no primeiro espaço da função, definir ela invariante, entendeu?
Sim.
E isso hoje eu vejo que isso é muito constraint, entendeu? Claro. É um constraint muito forte. Que a gente não tá, a gente basicamente você perde correlações dentro do grafo, você perde um monte de coisas interessantes quando você faz essa forçação de barra. E tirando essa forçação de barra, você tem uma coisa muito mais expressiva, entendeu?
Eu sei que mesmo correndo o risco de piorar demais a situação, você vê algum impedimento desse formalismo ser aplicado também a grafos com arestas não binárias, são arestas binárias?
Não, isso aqui funciona para qualquer definição de grafo. É basicamente voltando... a ideia aqui é voltar à definição original do que é ser... Só definir permutation invariant. Volta à definição original do que é uma probabilidade do grafo e esquece o resto. Pode ser qualquer coisa, pode botar o grafo, pode ter multigrafo, pode ter loops, pode ter arestas com valores, qualquer valor, a aresta pode ser multidimensional. O que você quiser funciona nesse caso.
Só vai ficando mais difícil.
Depende, falar a verdade depende. Às vezes se você botar um grafo mais rico, com mais atributos, a tarefa fica mais fácil do que se você tivesse tirado.
Mais perguntas?
pergunta. Eu queria saber se esse tipo de insight pode ser útil ou já foi útil para tarefas de aprendizado com imagens. Assim, sei lá, se tem alguma forma de você pegar uma imagem, usar alguma técnica de reconhecimento que reconstrua um gráfico dos pixels, que identifique superfícies, objetos diferentes.
Sim. Em imagens, o problema principal hoje é um problema parecido, que é a invariância, né? Achar uma invariância que seja rotação, translation invariance da CNN mas rotação, scaling, invariância background. Por exemplo, você tem um cachorro aqui e o background pode mudar. Mas o cachorro é o mesmo, entendeu? É invariante ao que tem atrás, né? E tem muitos trabalhos nessa área, de como é que você acha invariâncias em imagens. Uma coisa engraçada é que o PSD, essa ideia de mostrar permutações, na verdade, é uma maneira que é parecido com a maneira como a gente de verdade treina Convolutional Neural Networks, porque a gente pega a imagem, a gente faz uma rotação arbitrária, faz um scaling arbitrário e dá para a rede neural. Então isso já se sabia que tinha uma relação com tentar fazer ela ser invariante a esse tipo de rotação, né, e scaling. Hoje em dia, basicamente, a gente entende que o principal problema de neural networks é aprender invariâncias. E que quem entender como é que a gente deve aprender invariâncias, otimizar essas funções melhor, vai ganhar neural networks, porque realmente esse é o problema.
Eu tenho uma pergunta, talvez seja ignorância minha, talvez seja uma pergunta estúpida, mas o que significa uma matriz de adjacência não binária?
É só que você tem, ao invés de valores zeros e uns, você tem um valor real, por exemplo. Poderia ser, por exemplo, a sua distância para um local. Entendeu?
Tem um resultado similar para uma matriz zeros e uns?
Os resultados todos que eu mostrei valem para qualquer definição de matriz, né? Então, a matriz pode viver no espaço ômega ou qualquer que funcione. Contanto que seja contável. E não contável, o teorema existe, o meu aluno vai começar a trabalhar nele, mas vai demorar um pouco, porque basicamente coisas contáveis e incontáveis em Measure Theory é quase a mesma coisa, só que o teorema é mais difícil de provar. Então, você tem que ter algumas assumptions sobre smoothness da função e tal. Basicamente, o que você faz é o seguinte: você fala assim, a função é smooth, nesse negócio aqui é quase como se fosse discreto. Então é discreto, então isso aqui é a prova. É basicamente o negócio assim.
Ok, mais perguntas? Então vamos agradecer o Bruno. Sim, última pergunta.
Tem alguma noção porque assim, você não consegue classificar para todos os gráficos se eles não são isomórficos, né?
Em teoria você conseguiria, sim, mas é muito caro. Porque a gente não sabe nenhum algoritmo que seja polinomial, né? Então,
sim. Mas eu digo, porque você treina a sua rede num conjunto finito de gráficos, né?
Sim.
E aí você tiver dois gráficos que não estão nesse conjunto e eles são quase isomórficos. Assim.
Sim.
Aí a perda é muito grande.
É uma boa pergunta. Depende do como é que as redes que você treinou. Se elas são muito diferentes, você vai ter uma perda provavelmente grande, porque a rede não vai entender que coisas que são pouco diferentes, na verdade, são muito diferentes. Especialmente, por exemplo, em moléculas é um caso muito sério. Porque você trocar um átomo, entendeu? Trocar um bound, você está mudando completamente a propriedade da molécula, né? E a rede neural precisa entender que esse bound aqui não faz diferença, mas esse outro aqui faz uma diferença danada. Diferença entre você tomar e melhorar e você tomar e morrer, né? Então você precisa dar exemplos, entendeu? Para a rede neural de coisas a diferença de vida e morte, basicamente, entendeu? E quanto menor as diferenças, melhor ela vai aprender que ela precisa separar essas coisas. As representações precisam ser bem diferentes.
Então vamos agradecer, Bruno, obrigado. Quem quiser assistir de novo com calma, está gravado no Facebook do PESC e os slides também vão estar disponíveis depois, ok?
E as referências, eu vou botar as referências todas nos slides.